Can you hear me? Yes. So, good afternoon, everybody. First of all, I would like to thank the organizing committee for the opportunity to present my work here. I'm Warlley, and I am a PhD student at Departamento de Física, Universidade Federal de Viçosa, which is here in Brazil. This is the collaborators of my work. And as I don't know much about Maurano fermions, I will talk about a much deeper thing, which is a possible application of topological insulators and a technique from optical physics. So I'll talk a little bit about Viçosa and the university I study. Here is where we are. Here is the state of Minas Gerais, which is next to Rio de Janeiro, right? And here is Viçosa, just going north from Rio de Janeiro. This is a photo of part of the campus, and here is the Department of Physics. So I will make a very brief introduction about topological insulators. The three-dimensional version were discovered in the past decade, and since then, they have been the subject of extensive research due to the very unique properties that they present, and they are quoted for applications in mainly in nano device, right? And some of the properties that they present is that they have a gapped book band structure, as you can see in this Harper's measurement. But due to the strong spin-orbit coupling, they can present metallic surface states which are protected by time-reversal symmetry. Of course, you can break time-reversal symmetry by applying magnetic field, for example, and this induces a gap here. These metallic surface states, they cannot be easily broken by some non-magnetical impurity, for example, or even deformations in the form of the sample. And they present a property called spin momentum locking, so that electrons can move in any direction in the surface, but they are always coupled to the spin. So the cruiser phenon are coupled. And backscattering are not allowed in the surface of topological insulators. So the electrons propagate without loss of energy, or with low loss of energy, or loss of electrons. So the topological insulators are quoted for application. Mainly in topological quantum computing, the electronic devices with low dissipation, and also in spintronics. Recently, it has been observed that you can make a spin injection in junctions of topological insulators with magnetic materials, right? And also you can convert a charge current into a spin current. This was observed very recently. And here we are trying to apply topological insulator particles in a technique which is called optical tweezers. I'll try to explain how it's worked. So you need a microscope, an optical microscope, which you put the particles you want to study here in in a cover slip with an glued O-ring, and inside the O-ring you put a solution with the particles at the micrometer size, right? The laser used has a wavelength of 1064 nanometers and a laser power of 25 milliwatts. Yeah, you can change this value if you want in the experiments, but all our measurements was made in this power. All right, the trapping of the particles consists mainly in the conservation of momentum, of linear momentum of light. So we know that light has linear momentum, and when it is or reflected or even absorbed, it transfers its momentum to the material. All right, so at the micrometer scale, this become appreciable. And if the refractive index of the material is higher than the refractive index of the surrounding medium, then when you have a Gaussian profile modulation for the intensity, a ray coming from this point will refract at the surface, all right, and being deflected towards the center of the sphere, resulting in a force acting in another direction due to the transferring of momentum, all right? So a light ray coming from this point also suffers refraction here, giving origin to a force in this direction. But as the intensity of the light beam is greater here than here, so the resulting force or the net force will be directed toward the focus of the light beam. So the light beam has to be highly focused for this technique to work, all right? And this force is called gradient force, and it is proportional to the gradient of the intensity of the light beam. So in this technique, another important force is that coming from radiation pressure, which is basically the reflection of light in the surface of the particle, and it is proportional to the intensity, and also absorption of light inside the material generates a radiation pressure, right? And this force tends, contrary to the gradient force that tends to attract the particle to the focus of the light beam, this radiation pressure force tends to deflect the particle away from the light beam. So you will always have a competition between the two forces, the gradient force and the radiation pressure. And this competition will dictate if the particle will be trapped or not. All right? Another important force that you have to remember in all experiments is the viscous force, known as Stokes force, which is proportional to negative of the velocity, right? So when you use the electric particle, usually most of the light beam will transmit through the surface and will be refracted. So you have a gradient force higher than the radiation pressure force. So this will lead to stable trapping of the particle, all right? And if you use a metallic particle, most of the light will be reflected at the surface, and you will have a radiation pressure dominating, and this particle won't be trapped, all right? The particle will be deflected. So this technique is well established. It was developed in the past century and is regularly used nowadays. And as metallic particle can be trapped, people will use dielectric particle in these experiments. So here I'll try to talk about some applications of optical tweezers. They are mainly used by biological physicists, but also by by biologists. And here, for example, they use the optical trapping to study surface membrane tension. Here, you can trap a dielectric particle and stretch the membrane and study its elastic properties. You can study the tension, right? It is mainly used for DNA studies. You can trap, you can attach the one tip of the DNA to to the the cover slip in your microscope, or even to uh, another one unfixed particle, all right? And the other particle you will trap with the optical tweezers, and then you can move this laser in order to stretch the DNA and study its mechanical properties, or even you can open, you can fix one side of the tip and fix trap the other and open a DNA. This is also doing. So the optical tweezers are also used in micro rheology, when you can trap a particle. Here you have this is a protein. If I think it's a protein, but you can trap a particle and make a fluid to flow and study rheological properties. You can study the viscosity of the fluid, but you have to you have to make the fluid to flow, or even move the stage or the cover slip. All right, so it is difficult to make and demands all on apparatus for doing this. So summarizing what I have said until now, if you put a dielectric particle in the microscope, then gradient force will dominate and there will be a particle trapping. Okay. If you try to put a metallic particle, it will be deflected away from the focus, and there won't be any trapping of the particle. So we can wonder about the effects of putting a topological insulator particle instead of a metallic or dielectric particle. All right. Thinking very simple, in a very simple way, the topological insulator particle is a dielectric particle with a very thin surface, which is metallic or just conductive. All right. So we have done that with we put dielectric particles in an optical tweezers, and we have observed an oscillatory motion. All right. So the gradient force and the radiation pressure competes in a way that no one win the competition always. All right. You have this competition all the time, and the particle keeps oscillating. All right. So in our experiments, we have used bismuth telluride, okay, and in order to obtain the particles, we have used a technique known as laser ablation, in which you put the bulk target here, which in this case is the bismuth telluride, and you hit it by shedding a highly energetic light beam that hits the target and rip some particles at the micrometer size. All right, that were our particles we have used. So I'll show you two videos. Sorry. So we have used video microscopy to analyze the movement of the particles. Here you can see a topological insulator particles oscillating towards the focus of the laser beam. All right. Unfortunately, we couldn't obtain perfectly spherical topological insulator particles. This is one of our objectives, one of our prospects for future, for continue this work, all right? And there's another video. Here you can see 4 topological insulator particles oscillating toward the focus of the light beam. And now a dielectric particle that we put here, you can see that it will be trapped in this point. So this is a dielectrical particle, and these are the topological insulator particles. You can see the difference from the video. All right, so here are our results, and we have observed that the topological insulator particles oscillate perpendicular to the focal plane of the laser beam, and the particles we have obtained by laser ablation are between 3 micrometers and 7 micrometers, and this graph is being shown for a particle with 4.2 micrometers. So here you can see the oscillation, which the amplitudes vary between 7 micrometers and 9 micrometers. So it wasn't expected this variation in the amplitude. We think this is related to the non-spherical form of the particles, all right, and also small deviations from the plane. As the particle is not spherical, it not always will oscillate in the plane. Sometimes it go out of the plane, all right? And also it can be small rotations due to the non-spherical form. You can see here that the closest approximation from the focus is 3.2 micrometers. So this is not a trapping like dielectrical particles, which are trapped exactly at the position equals to 0. And the one important thing that we have to notice is that the period of oscillations is well defined. It's about 3.52, all right? And this is very important for applications of this method for high accuracy measurements. So here we propose a very simple theoretical model to explain the motion of the particles. Here in red you can see this is the laser beam. So this is the focus of the laser beam, and it has a waist. Sorry by the pronunciation. This waist, and this waist is given by this formula. All right, so it increases as far as you go away from the focal plane. And here are the topological insulator particle, which oscillates in the parallel to the focal plane. Right, the laser is propagating from below to above. So as I said before, the intensity is modulated by a Gaussian profile. All right, and as the radiation pressure force is proportional to the intensity of light, we have this expression for the radiation pressure, directly proportional, and the gradient force we can obtain by deriving this expression. All right, this constant is the maximum value for this force, and summing up these two equations, we can find a total optical force acting on the particles. All right. So here is a graphic of these forces. You can see in green the behavior of the radiation pressure. All right, which is always positive, then deflecting the particle always from the light beam, and here is the gradient force, which is always negative. And summing up these two behavior, you have in red the resulting optical force. All right, you can see that it changes sign from here. The position where the force change sign is given by this equation, just taking force equals to 0, and this is the point where would be the equilibrium point. All right, but as you can see here, the movement it's not harmonic. All right, so it is difficult to obtain expressions. So by measuring the position of the particles and knowing the the density of the particles and its volume, we can measure the force, all right? And here we fit this force with our model. It is a good fitting, as you can see, and we can obtain the three parameters. All right, this is the waste, the beam waste. From using this value, I actually did an average of this value for many cycles. This is just one cycle of oscillation, all right? And making the average through many cycles, we can use this expression here to calculate the omega 0, which is I think you can see here, but there is a 0 index. We can calculate the omega 0, all right, which has a predicted value because we know the wavelength of the light beam. So we have a value which is close. And for the experiments made by biological physics using this optical tweezers technique, this is a good agreement, right? So here we have done some averages to observe the dependence of the strength of these forces with the diameter of the topological insulator particles. And as the diameter of the particle increases, you can see that the average optical force also increases. But here we have separated the repulsive motion, which is given by these open circles, and the attractive motion, which is given by the black circles. And you can see that in the repulsive motion, where you have radiation pressure dominating the movement, the force increases rapidly, or faster than in the other case. All right. So in this range we have analyzed. We have also plotted the period of oscillation with the diameter of the particle, and we can see that this period decreases with diameter. All right. So even the movement of the particle being not harmonic, we tried in a first approximation to try to describe the frequency. We have proposed a simple model and taking the gradient force proportional to the radius, the cubic of the radius, because the gradient force is related with the bulk or the volume of the particles, and we took the radiation pressure to be proportional to the area, as it is a radiation pressure. So and the Stokes force, it is a well-known expression which is proportional to the radius of the particle. All right. So taking this harmonic description, we obtain an expression and have plotted with the experimental data, and it was a good fitting. Even the interaction of light with the topological insulators being more complex that we understand now. This was a relatively good fitting, and we have obtained these parameters. This work is in the beginning yet. We have much thing to do. And I think that the principal thing to do is to obtain more spherical particles, right? To obtain more precise results, right? So where can this method be applied, right? Well, as I said before, the optical tweezers technique is used very much for measurements using DNA. So what they usually do to measure the property, they oscillate the stage here, the cover slip, which is attached to the DNA. All right. So all this you have to change all the setup in order to oscillate the stage and obtain its results. So it will be much more simple to use topological insulator particles so that the oscillation would occur naturally. And you could control the frequency with the size of the particles, and also by changing the intensity of the light beam. Right? This could be used also in micro rheology. In this work, they had to use two optical beams in order to make a particle oscillate between them. They were trying to measure the viscosity and some other rheology related properties. And in order to make a particle oscillate, they had to put two optical beams. This could be made in a much more simple way by using topological insulator particles, of course. So, concluding, we have observed that bismuth-telluride particles oscillate perpendicular to the optical axis when subjected to a light beam, and the frequency remains constant in various oscillations, and you can control this frequency with the size of the particles, which is a powerful tool. And we need more spherical shaped particles to obtain more precise results, and also for highly precise applications of the method. And we also want to make this analysis with other topological insulator composites, because it can manifest these properties more intensely. And also we want to functionalize the topological insulator particles, which is maybe cover it with a protein or some other object to attach the DNA particles, the DNA molecules. And that's it. This work is available in arXiv if someone is interested. And thank you very much for the attention. And I would like to thank you, just a second, I would like to thank the funding agencies, CAPES, CNPq, and FAPEMIC for supporting this work. Thank you very much.
Questions, please. Yes.
Can you maybe summarize which property of